All right, so this is more applications of the definite integral and the fundamental theorem of calculus, specifically understanding it as an exact change in my function. All right, so looking at it and interpreting it using its area. So we're going to be looking a lot with the area of the function in this case. All right, so using the FTC, which remember means fundamental theorem of calculus, to solve the definite integral. All right, specifically we're looking at it to solve the exact change in a function. All right, so suppose we're given a derivative, a rate of change function. All right, we can find the original function using the initial value problem if we're given an initial value, which is what we did in 5.1, right? We found initial values in the original function, right, and then used it. In this case, I don't have to find my original function exactly, but I can still find a change in my original function, and that leads us to the net change formula, or the net change theorem. And basically, it's just a special case of my fundamental theorem of calculus. If you go back and look at the fundamental theorem of calculus, it works for any continuous function from point A to point B, meaning the function could be a derivative. It might not be a derivative. It might be a second derivative, third derivative, fourth derivative. It might not be any derivative at all, all right, and it works. All right, the fundamental theorem of calculus works for any function so long as it's continuous. Well, the net change theorem is specifically looking at the function if it's a derivative. So what we're integrating, we know, is a derivative, and we know the derivative is continuous. We know the original function, which we're actually not going to find. Right, that would be initial value problems, which we did in 4.1. We're actually not going to find it. But what we are going to find is an exact change in that original function between A and B. All right, so we're given a derivative. My derivative is the f prime of f. I'm integrating it from A to B. This is really still an antiderivative, which would be any possible function that's f of x. All right, we usually do the case where we leave off the constant. So we're not technically finding f of x. We're finding most of it, all but the constant. All right, but the next step, it doesn't matter that we don't find the constant, because remember, the next step in the fundamental theorem of calculus is I take my upper value and I plug it in my antiderivative. I take my lower value and I plug it in my antiderivative. Well, my antiderivative stands for my original function, which again, I don't have. But this is equal to if I had it and I plugged B in and I plug A in, because when I subtract, I would have a constant in the B part and the first part and a constant in the second part, and they cancel each other out. So it doesn't matter that I don't find the constant. This is still going to find the exact change in my original function from point A to point B, and that's what this net change theorem means. All right, so if we're given a derivative of our function, we integrate it from A to B. That integral finds the exact change in the function. What it is, it's the net change as x changes from A to B. And that net change could be positive, it can be negative, or it could be zero. Right, I could change, right? And what it comes down to is the area above is where it's increasing, I'm adding to it. Area below would be negative, and if I had the same area above and below, it could technically zero out, all right? So this answer could be, the net change could be a positive, a gain, it could be a negative, it could be a loss, or it could be zero, neither a gain nor a loss, over the entire piece of function that I'm looking at. All right, so graphically, so I'm going to talk about it graphically because the first few examples are going to be just graphical applications. All we're given is the graph of my derivative. All right, so we're going to be given the derivative. All right. And some of the questions will actually be throwbacks. If you remember from chapter 3, we understood the graph of the derivative tells us a lot about the original function. It tells us when the original function is increasing, decreasing, has max and mins. We're going to, again, incorporate that a little bit here. We're going to add to it because now we know what the area under the derivative gives us. All right, so I'm going to kind of add that all in here graphically. So I'm going to graph a derivative. So these would be the x values. This would be the derivative, which would stand for a change in y over a change in x, a rate of change, right? Dollars per hour, people per year. Again, it would stand for some type of rate. All right, so suppose my function looks like this. All right, so this again, remember, is the derivative, the rate of change function. So if you remember, I'm going to mark these points off. All right, these points where it hits my x-axis, I'm going to call it C1 and C2. And the reason why I'm calling it C1 and C2 is because those values are the criticals of the original f of x function. Right? Those are the criticals. It's when my derivative equals 0, right? Those are where my critical values are, which means those are my possible maxes and mins, which that's not new. We covered this in chapter 3. It's been a while, all right, because that was towards the beginning of the semester, but that was when we covered it, right? And then when our derivative is positive, our function's increasing. When our derivative is negative, our function's decreasing. And so over this piece, from 0 to that first critical value, this would be positive, right? Which means f of x is increasing. Well, now we know exactly how much it increases by. All right, once I find this area, this total area here, right, that area under the f prime of x, under the derivative from x equals 0 to x equals my first critical value, is the net increase, so my function's increasing, of f of x over those intervals. Right? It finds f of C1 minus f of 0. That's what that area represents, which I can find with my integration. Right? That's what that net change theorem is telling me. And so if this were profit, suppose this was profit, this area would represent the total gain in profit from 0 to C1, whatever 0 and C1 represent. All right, and then it would stop, all right, at the critical value, right? That's what the critical value means. It's a stopping point. And then it switches to decrease, right? And I'm negative area here, which means my original function, which I don't have, this is the derivative I have, but I know if the derivative is negative, my original function is decreasing. All right, and again, this total area would represent decrease. All right, so the area from C1 to C2, between those two critical values, would be a net loss, right? It would be a decrease. We would know the net decrease of f of x from C1 to C2. All right, and again, it would represent a loss. All right, as I would take my C2 minus my f of C1, and it should come out negative. And it's exactly whatever this area is. And so again, if this were profit, between my first critical value and my second critical value, they lost profit. Profit was decreasing, and this area tells me exactly how much profit decreased by. All right, then after that, all right, again, so if I suppose I stop here at B, I'm gaining again. So this is positive area, and so we'd be gaining, all right? It would be a net gain. Right? So we'd be adding to the area. So if I integrated, and I'll just integrate from the area I have shaded in, so I'm going to erase this so I can write some more information down. All right, so if I integrated from 0 to my second critical value, all right, I took the integration of this derivative from 0 to the critical value 2. This would be the positive area. All right, that would be this area. And I would subtract away this negative area. All right, I would take my gains and subtract away my losses, and that would give me my net change, which would represent, I take my critical value and then add 0 from 0 to 2. And again, it could come out positive, it could come out negative, it could come out 0 if the two areas are the same, right? If I had more gains, it would come out positive. If I had more loss, it would come out negative. If gains and losses were the same, it could come out 0. The net change would be 0. I gained as much as I lost over that interval, all right? And so that's what we're going to be looking at in these cases. The other thing I want to make note of is, again, it's a throwback question, actually. But you should understand maxes and mins, right? So my relative max or mins can only happen at critical values. So in this case, the possible max and mins would be at my two critical points, C1, C2. Well, it should make sense. A max should occur after a gain, right? This would be a gain, this would be an increase, stopped, and then this would be a decrease. And so my first critical value is a relative max because it follows a net gain, right? And then it goes into a net loss. So it changes from gaining to losing, so that would be a maximum. My second critical value would be my relative minimum. Again, because it would follow a net loss, right? This would be a loss, and it's following a net loss, and then on the other side I'm gaining, and so that would be minimum, right? I'd be going down and then back up again because I switched from decrease to increase. Absolutes, right, which we're going to want to find absolute max and mins. Well, absolutes either are at my critical values or my endpoints, right? Which in this case my endpoint would be 0 and B, and I'd have to figure out, well, how much. So when I'm looking for absolute max or absolute mins, well, they can happen at the endpoints, which would be 0 and B, or the critical points, which would be at critical point 1, critical point 2. And then I'd have to see is, well, how much gain or loss do I have altogether? Do I gain, which of those points would give me the most gain? That would be my absolute max. And which of those points give me my most loss, most decrease? And that would be my minimum. And then I'd have to test it using my area, use my net gain change areas. All right, and again, we'll do examples of that in the next set of notes. This is sort of setting it up. And so the next set of notes, what we're going to be given is a derivative equation. It's a graph, and we'll know what the areas are above and below and where the critical points land. And then based on that, we're going to answer questions. And some of them aren't new. They're old questions from Chapter 3. We're just going to look at them now more in depth because now I have an understanding of what the area under the curve is. All right, so I'm going to stop there, and in the next set of notes will be applications of this. We're going to be applying this.